Welcome to lecture 14 of Power System Protection course. In the last class, that is in lecture number 13, we discussed the general principles of distance relay, that is the protection scheme used in the transmission system. So first we put the universal torque equation, and from which we derived the equation for impedance relay, and then we have found the operating characteristic of impedance relay, and also how the fault characteristic will be put in that impedance relay, and it can be found the restraining region and the trip region. And similarly, uh, we have seen the impact of under normal load condition, how the impedance relay behaves, and during the arcing fault, how it becomes under reach. So percentage under reach, also we have seen the equation of percentage under reach, and then we have seen uh, how it will behave under the arcing fault. And now in this lecture, we'll see how the impedance relay behaves under the power swing condition when some system disturbance occurs. At that time, power swing happens in the network. So power flow in the line, it swings, and because of the swing in the angle and the velocity of the speed of the generator, the rotary angle of the generator. So let us see how it affects, and then we'll talk about other different types of distance relays, that is like your reactance relay and more relay. In this lecture particularly, we'll cover the reactance relay. So let us start with, and we'll see the performance of the simple impedance relay during the power swing. So during the power swing, how the simple impedance relay in fact behaves. Let us see. Okay, so this is a transmission line where we can see here we have two sources, EA and EB, right? And EB is considered as a reference phasor, and EA is making an angle of delta, and ZSA is the source impedance at bus A. Let us say this is bus A and this is bus B. Okay, and so ZSB is the source impedance of the source EB, right? And ZL is the transmission line impedance. And we can see here that your VR and IR, their IR is the current measured by the CT, which is being fed to the relay, and VR, which is measured by the PT, but the VT is fed to the relay as well. So therefore it is marked as VR and IR. Okay, so the relay is connected at bus A. Okay, so now let us see. Obviously, if we can express the impedance seen by the relay, that is ZR, as a function of delta, then obviously under power swing we can find what will be the exact characteristic of ZR, right? Impedance seen by the relay during power swing, and accordingly we can find whether it falls in the trip region or whether it is in the restraining region. So accordingly we can decide the behavior of impedance relay under power swing. Okay, so let us say, and let us do that. So let us first find the current IR that is seen by the relay in the form of the different voltages and the impedances. So IR, I can write it as EA delta minus EB. So I can write IR is equal to EA delta minus EB divided by ZT. So here EA is your voltage, that is internal voltage of generator A, that is connected at bus A, and EB is your internal voltage at bus B, and ZT is your total impedance, that is ZSA plus ZL plus ZSB. So your ZT is ZSA plus ZL plus ZSB, right? And from this equation I can write, or else I can write VR. From at this point I can write the equation of VR, that is VR equal to EA delta minus IR ZSA. So the voltage at bus A will be the VR, that is voltage seen by the relay, and that will be nothing but EA delta minus IR ZSA. Okay. Now from this equation, from this equation I can find just by multiplying ZT and dividing IR at both the side, or I'll find that ZT plus EB by IR minus EA by IR is equal to 0. Okay. And from this equation, from the equation of VR, I can find just by dividing IR both the side, left hand side and right hand side, I will find VR by IR, which is nothing but, this will become VR by IR, which is nothing but equal to ZR, and ZR will be equal to minus ZSA. Okay, this IR is divided, so plus EA by IR, right? Now we can see this ZR as a function of delta, right? So ZR is a function of delta. Now we can see it is minus ZSA plus EA delta by IR, right? So EA by IR I can write in terms of ZT plus EB by IR. Okay, so now we can see here that obviously your ZR is V by VR by IR. So let us see this swing curves. Now we can see that how delta is varying when the power swing happens, right? So if we'll plot your rotor angle, that is delta, okay, delta versus time, here time in the x-axis. Now after plotting this, for unstable power swing, obviously your delta will diverge. It will increase very drastically, right? Okay, and for your small disturbance, that is we call it stable power swing. For stable power swing, it will swing for some time, then it will stabilize, right? So this is how the power swing happens. And when, if we'll express your ZR as function of delta, that is impedance seen by relay as function of delta, then easily we can see where your impedance is lying during the power swing, right? So already we have seen this, right, in these equations, and let us go forward. These equations already we have discussed, and we found that your ZR is a function of delta, right? Now let us plot this ZR, that is impedance seen by the relay. Okay, so let us see it. So now here we can see that we are now plotting different impedances, right? So let us plot first your ZRA or ZR simply, right? That is VRIR, that is the impedance seen by relay at location A, okay, and that is equal to nothing but, already we derived it, minus ZSA plus EA delta by IR, and here which curve it will show. Now let us plot it. So it will be minus ZSA. So if we'll start from here, origin, then minus ZSA will be this, right? then your plus EA by IR, this is nothing but what? This is nothing but your EA by IR. Already I told that this is your uh, ZT. Sorry, let us see it. It will be your ZT plus EB by this is your ZT plus EB by IR, right? That will give me uh, EA by IR. So EA by IR is nothing. I can write here, or you can go back and see it in the last slide. So EA by IR is nothing but ZT plus EB by IR, and ZT is nothing but ZSA plus ZL plus ZSB. So if we'll see it, so ZT is the sum of minus ZSA plus ZL plus ZSB. So this is the magnitude of ZT, right? So now I can see ZT here, ZT plus your EB by IR, right? That will give me EA by IA, EA by IR, right? So this is your EA by IR, okay. So now after finding EA by IR, just by adding minus ZSA, I can get ZRA. Okay. So now just add minus ZSA. Minus ZSA is this, right? This is your minus ZSA plus EA by IR, right? EA by IR is this. So this is your ZR. Okay. So now this is your ZR, and this is your EA by IR, this is your EB by IR. So between EB by IR and EA by IR, the angle is delta, right? So when delta is this much, your ZR is lying here, right? As your delta will decrease, okay, gradually it will decrease. It will decrease means your ZR will move in this direction, right? Somewhere here. If at this point your delta is less, right, as compared to delta at this point, right? So therefore, it will gradually go outside the as the power swing will go down, it will gradually fall in the restraining region, and your relay will restrain. And as your power swing will increase, that is delta will increase. As your delta will increase, your ZR will lie somewhere here, right? So this is the delta where it is increased. It is greater than this delta, and which will lie in the trip region. We can see this curve. this is your operating characteristic of the impedance relay, right? Operating characteristic. Okay. So under this operating characteristic, under this circle, whichever point will lie, ZR will lie, that will give us the trip signal, and outside it will give us the restraining signal. Now we can see as your swing is decreasing, it is the magnitude is less, the swing magnitude is less, that means delta is less, and so therefore your ZR will lie outside the trip region, that is in the restraining region, right? And when the swing is more, it is greater, the magnitude is high, your delta will increase, and therefore your ZR will lie inside the trip region, right? It is very clearly understandable. Okay, this is your trip region, this is your restraining region, right? So therefore, when your delta magnitude swing, the swing of the delta magnitude is less, it will lie in the restraining region. Okay, now let us see how it looks when, because previously we assumed that EA, the magnitude of EA is equal to EB, that is the under the flat voltage condition. Okay, when your voltage regulation is very less, okay, voltage regulation is 0, you can say, right? So in fact, that under that condition, that your ZR characteristic under power swing will become a straight line, right? We can see here, right? For EA equal to EB, it is a straight line. But when your EA becomes greater than AB, now we can see here under this condition, this is your EA by IR, this is your EB by, this is your EB by IR, this is your EA by IR, right? So now if EA is greater than EB, your curve, your characteristic, ZR characteristic will look like this, like a curve, right? Okay, so this is like this. And when your EA is less than EB, it is below the straight line, right? It will become like this. Okay. It is little curved, but it is like this. And we can see here very easily the explanations. Now we can see the impedance relay, the trip region and the restraining region. If your Z lies inside the trip region, then ZR lies in the trip region, it trips. If it is outside the trip region, it restrains, right? So you can easily observe here for EA greater than AB, the even for larger swing, it happens that it sometimes doesn't trip, right? Okay, so therefore the voltages are kept flat, right? There it is the main, it is the one of the objective. So okay, this is all about your impedance relay. Now let us talk about the reactance relay. So how this reactance relay will, as the name suggests, previously the name suggested, as per the name of the relay, it was impedance relay, and we are talking about the impedance, and the comparison was between the impedance of the line, the set impedance, and between the seen impedance, the impedance seen by the relay, that is ZR. And in case of impedance relay, we have seen the comparison is between ZR and Z set, right? So if your ZR is less than Z set, then it will trip, right? And if your ZR is greater than Z set, then it will restrain. So this is the law we found, right? Trip law. So this is for the impedance relay, and it compares the magnitude of the impedance, in fact, right? It is not the angle, it is the magnitude of the impedance. Now, as the name suggests here, reactance relay. So obviously this will be this will consider the reactance seen by the relay, and it will compare the set reactance, the reactance set in the relay. Okay, so let us see, and let us first derive the equation for reactance relay from the universal equation, universal torque equation. So your universal torque equation is this, right? That is T equal to K1 IR square plus K2 VR square, K3 VR IR cos of theta minus tau plus K4. Already we have seen this. Now in this case we'll take some assumptions. So that assumption is like we'll consider here the K2 as your 0. Okay, so if we'll set K2 equal to 0, make K1 positive and make K3 negative. So K1 will take positive and K3 is negative, right? And this K2 is equal to 0. So now by setting this, and obviously we know the assumption that K4 is neglected when the relay is on the verge of operation, right? So therefore we can say the trip law is like this: if K1 IR square is greater than K3 VR IR cos of theta. So at the verge of operation it will be K1 IR square equal to K3 VR IR cos of theta minus tau, right? And when the relay starts operating, this will become greater. Okay, so because this is your operating torque, so this current will provide the operating torque, and this will provide the restraining torque. So therefore your K1 IR square should be greater than the restraining torque given by the directional element, right? So therefore I can write if K1 IR square is greater than K3 VR IR cos of theta minus tau, that is the torque developed due to the current element is greater than the torque developed due to the directional element, then it will trip, else it will restrain, right? Now we can see how this is your uh, phasor diagram, right? Already we have seen this, how the torque is developed for directional element and how the torque is developed for current element. Already we know this, right? So now if we'll see K3 VR IR cos theta minus tau is, then from this equation we'll see that K3 VR IR cos theta minus tau should be less than K1 IR square. And from this equation again I'll find VR IR divided by IR square. I can write it as cos theta minus tau less than K1 K3. Just by rearranging this equation I will find this equation, right? Now VR by IR will be VR by IR cos theta minus tau should be less than K1 by K3, right? So now if I'll make this tau, that means VR by IR, already we know that this is ZR, which is the impedance seen by the relay, that is Z sin, right? So therefore I can write Z sin cos of theta minus tau less than K1 K3. Now if I'll substitute this tau as 90 degrees, somehow I can make the MT, that is maximum torque angle, as 90 degree, right? Then what happens? In fact, in practice, we can make this MT 90 degree by adjusting the the resistance and reactance in the coil by putting the resistance and capacitance in the pressure coil, right? So if I'll make this MT 90 degree, then what happens? If we set MT of the directional element to be 90 degree, then and let the K1 and K3 be Xn, then what we'll get? What we'll get? We'll get Z sin cos of theta minus 90 degree is less than Xn, right? So here we can make this tau, this angle, as 90 degree. How we can make 90 degree? Just by putting a high resistance in the pressure coil, we can make this IPC, that is approximately in reference with BPC, right? So if this IPC will lie in VPC, it will move to VPC, then your tau will also move to an angle of 90 degree, right? So this tau will become 90 degree. So this can be possible by adding a high resistance in the pressure coil. So we'll see in the next slide these things. So now your equation became Z sin cos of theta minus 90 degree is less than Xn, and from this Z sin cos theta minus 90 degree is nothing but Z sin sin theta, and that is equal to X sin. Okay, so Z sin sin theta is your X and Z sin cos theta is your R. So your Z sin sin theta now became the X sin, that is the reactance seen by the relay, right? Reactance seen by the relay. Okay, so now I can say that we finally get the trip law as X sin is less than Xn. If your Xn, that is the reactance seen by the relay, is less than the set value of the reactance, then it trips, else it restrains. Okay, so now this characteristic, from the characteristic we can see, if we'll plot this x and plot this in xr plane or rx plane, then we can see that your set value xn is here, right? This will give us the set value, right? And below this it will be tripping, and above this it will be restraining. If your x seen by the relay is lying outside this curve, that will restrain the relay operation, and if it is below this curve, then it will trip. Okay, so now your line fault characteristic, if it is plotted, right, it is a Z, right, ZR or ZC you can say, and this angle is your theta. Okay, this is your theta, and ZR sine theta will give us XR, right? So obviously wherever it will be, your fault location will be, suppose it lies here, then your XR will be here, and it will be in the restraining region, right? Similarly, if it lies here somewhere, then it is lies in the trip region. So that is how we can see. And how we can make 90 degree, that tau equal to 90 degree, just by making IPC or IPC in reference with VPC. We can make this maximum torque line, this empty line as 90 degree with respect to VPC, and that is this tau will become 90 degree, right? And here theta is nothing but, theta is your angle between VPC and ICC. Okay, so this is the phasor diagram, and under this condition we found the Trief law. Okay, so this is how this relay can be implemented now using these equations. Right, so let us see the implementation of reactance relay using the induction cup structure. So you can see here the electromechanical structure of reactance relay. Here it is the induction cup which is connected with a bar, right? And as soon as this induction cup moves or rotates, it touches these trip contacts and it sends the trip signal to the circuit breaker. So now the question is how the torque is developed in this induction cup. So previously we have seen that in case of overcurrent relay, it was aluminum disc, and here it is induction cup, right? So in fact, when we are using the multiple poles, we need a cylindrical structure. Therefore, the cylindrical structure, we cannot make it a very heavy weight. So in order to make that cylindrical structure very lightweight, so it was made a cup shape, right? So inside it is completely hollow, and outside just aluminum sheet, and it is made like an induction cup. And we have 4 poles, we can see here, right? 4 electromagnets. Now the question is how to connect these electromagnets. So one of the electromagnet is connected to VR. That means your voltage measured by the PT is fed to this coil, that is called the pressure coil. And in order to make the current flowing through this in phase with the voltage, so we have put one resistance, high resistance, that is very much greater than XL, and so your MTA, your maximum torque angle, will become 90 degree, right? Okay, and now in the other side we inject the current. Here IR is injected. Now IR is injected in 3 of the electromagnets, right? And out of these 3, 2 of the electromagnets are known as the polarizing current coil, because it helps with respect to each other producing the torque, and therefore, and one of the electromagnet is known as the operating current coil, where we can adjust by using the resistance. Here the resistance and the capacitance, by adjusting this resistance and capacitance, we can change the angle theta. So that is, theta is the angle between VPC and ICC, right? Okay, so that is nothing but, we can say, VR and IR. So angle between VR and IR can be adjusted using R and C. Now all these electromagnets will produce flux, and because of this interaction of this flux, it will produce the torque on this induction curve. Now how it will produce the torque? Okay. Now the flux produced by this pressure coil and the current and the flux produced by this polarizing current coil. Obviously, let us say it is giving an torque in this direction, and similarly, because the current also the flux will be in the same direction of the because of the polarizing current. This is flux due to the polarizing current, and therefore your torque produced due to the flux interaction of the flux between the restraining coil and the polarizing coil will be again in this direction, right? And now the interaction of the flux due to the operating current coil and the polarizing current will be exactly in the opposite direction, right? And that is known as the operating torque, and in because of the restraining coil and the polarizing coil, it is the restraining torque. So the torque produced by the interaction of the flux due to operating coil and the polarizing current will be exactly opposite to the torque produced due to the interaction of the flux because of the restraining coil and restraining or pressure coil, and the polarizing coil will be exactly opposite. So now we can see it in the diagram very clearly. Now this is your torque produced due to the interaction of the flux because of the pressure coil and the polarizing current coils, this one and this one. So therefore these are the restraining torques, and this is your restraining torque. And now these torques that is produced due to the interaction of the flux due to operating current coil and the polarizing current coils is this, and that is known as the operating torque. Okay, so this is your operating torque, and they are opposing to each other. When your operating torque becomes greater than your restraining torque, at that time your induction curve moves and your trip contact is closed. So this is how your reactance relay is operated, right? And it is in fact implemented using the induction curve structure. Now we'll see the performance of the reactance relay during normal load flow condition. So under normal load flow condition, as we already have discussed in case of impedance relay as well. So under normal load condition, your impedance seen by the relay will be just little bit capacitive, and it lies close to the R axis, right? And because of that it lies in the trip region, as we can see from here. It lies in the trip region, right? So therefore under normal load condition, there is a chance that your reactance relay, not chance, your reactance relay always trips under normal load condition, right? So reactance relay always trips normal load condition, right? So how to avoid this condition? This condition can be avoided just by putting one directional element uh, or one impedance element which will avoid this impedance relay along with this reactance relay, which will avoid the tripping of this reactance relay under normal load condition. Now the question is, if we'll put the impedance relay along with this reactance relay, now what is the point point of using this reactance relay? Is this relay is in fact important? In fact, it is important. Why it is important, we'll see in the next slide. Because it very well it operates during the arcing fault. Because already we have seen Under arcing fault, your impedance relay doesn't operate properly. It has some underreach problem, right? But in case of reactance relay, when the arcing fault is there, because the fault is always arcing in nature most of the time. So under arcing fault condition, this reactance relay works well. Therefore, the combination of both the impedance relay and the reactance relay will give the operation suitable. So one is suitable for the arcing relay and other one is suitable for normal loading condition, right? Okay. So now we can see here that when there is a fault resistance at B, at point B, the resistance will be added to the impedance seen by the relay, right? Now your impedance seen by the relay will be this, and the reactance for this particular impedance seen by the relay, that is the reactance seen by the relay, will be here, right? So that means that at the boundary condition also there is no underreach problem, right? So the reactance seen by the relay will be exactly matching with the set value, right? So there is no underreach problem, right? Wherever it may be, right? So under that suppose your fault lies here somewhere, right? Under fault characteristic, then at this point if your arcing resistance is this, then obviously your reactance will lie here, and which is less than xn, and it is in the trip region, right? So therefore there is no underreach problem in the reactance relay. So the combination of reactance relay and the impedance relay gives a suitable protection measure. One is providing under normal load condition suitable application, and reactance relay is providing suitable application under arcing fault. So the combination is the most suitable. So now we can see the directional property exhibited by the reactance relay. In fact, the reactance relay doesn't provide the directional property. We can see here the region of protection here, it covers all, right? So therefore under forward direction also it operates up to the limit, up to the set value, and in the reverse direction it operates, in fact we can say a whole region, right? There is no limit in the reverse direction. So the directional property, in fact, it doesn't show. And we can see here the directional property, right? Under forward fault it is under first quadrant, and under reverse fault it is in the third quadrant, so it is in the trip region as well, right? Okay, so now we can see the performance of the reactance relay during power swing, under power swing condition, how it performs. So already we have derived the equations and the curves, that is the impedance seen by the relay during power swing. It is a straight line when your EA is equal to EB, right? So under the condition that EA is equal to EB, the magnitude of EA is equal to magnitude of EB. Under that condition your power swing curve is a straight line, and when your EA becomes greater than EB, it is a curve at the upper side, and similarly when your EA becomes less than EB, it is a curved characteristic, right? EA is less than EB below the straight line, right? Now from these characteristics we can easily find where the ZR is lying, and from that we can find the XR. In fact, the below curves will give this when your EA is less than AB, and also for EA equal to EB most of the portion, in fact it gives it lies in the trip region. So therefore, under the power swing condition, this relay is not at all suitable. It will give always trip command to the circuit breaker, right? So therefore, it is not at all suitable under power swing condition, right? Not suitable under power swing condition. So as we can see, the area covered by the trip region is very high, right? Power swing condition. Therefore, it is not suitable. Therefore, we must devise or we must design a relay which covers a very less area as trip region, and therefore your swing curve doesn't much of the swing characteristic doesn't or locus of the swing power swing doesn't lie or doesn't fall under the trip region. So that gives the best result for the power swing condition. So we'll see in the next class another type of relay which is the most suitable for the power swing condition, and that is the Moore relay, right? We'll see in the next class. We'll stop here. So thank you very much for your kind attention. Thanks a lot for